Okay, gentlemen, continuing on with our polynomial functions, we are going to now look at example number 2 here. You should first recognize that it is a polynomial function. All of your exponents are non-negative integers. We have our exponent of our 3, we have our exponent of 2, and we have the implied exponent of 1 here. So let's first look at what the overall degree of this polynomial is. If we were to multiply out all of those terms, we would end up with an x to the 6th, 3 and the 2 and the 1. Remember, if you're multiplying like bases, you add your exponents, so you'd have an x to the 6th. And our leading coefficient is negative, so it would be a negative x to the 6th. Or a negative x even, which means that our overall graph should look like a negative x squared, where our end behavior for a negative x squared is the ends of our graph should be going down towards a negative infinity. Our y value should be going down towards a negative infinity. If we look at our x-intercepts, what our roots are, we have a x-intercept or a root at x equal to 0, at x equal to 4, and at x equal to a negative 2. So let me just sketch those on here real quick. So an x-intercept at 0, an x-intercept at 4, and an x-intercept at a negative 2. So if we were to look at the behavior at those individual roots, what is going on as we are getting close to those individual values? So if we look at the behavior as we approach x equal to 0, and x equal to 0 came from that factor of a negative x cubed. So we already know that the behavior around x equal to 0 should look like an x cubed graph, okay? But if we want to be a little more specific about that behavior, then we can take that value of 0 and we can plug it into the other x's of the equation except for where it came from, and it came from that negative x cubed. So we're going to leave that term alone, and we're going to plug 0 in for the other x's. So 0 minus 4 squared, 0 plus 2, and we end up getting a 16 here, a 2 here, or overall a negative 32 x cubed. So the behavior of our graph as we get close to the x-intercept of x equal to 0 is taking on the shape of the graph of a negative 32 x cubed. Or if we're just generalizing that graph, it would be a reflected x cubed graph. Okay. So let me just sketch that on here. So as we're approaching x equal to 0, a negative x cubed graph would look something like that. Okay? And now if we look at the behavior around the other roots, let's look at the behavior as we approach x equal to 4. Well, x equal to 4 came from that factor of x minus 4 squared. So because of that multiplicity of 2, we already know that around x equal to 4, it should be taking on the shape of an x squared graph. A little more specific to that behavior is if we take 4 and we plug it into the other x's in the equation, except for where it came from. So if I plug in a 4 for x here, and if I plug in a 4 here to that other x, here we have a negative 64, here we have 6, and that is what? 24, 36, a negative 384, x minus 4 squared. So as we are approaching x equal to 4, the behavior of our graph is taking on the shape of a negative 384, x minus 4 squared. Or more specifically, it's taking on the graph of a negative x squared graph, an upside down parabola. And so if we were to sketch that around x equal to 4, this upside down U shape, this upside down parabola. And then the last factor of that x equal to a negative 2, and I'm just going to come down over here. So for that x equal to a negative 2, which came from the factor of x plus 2, so I'm going to leave that factor alone. And if I want to be a little more specific about the behavior as we get close to that x-intercept, I'm going to take the value of a negative 2 and I'm going to plug it into the other x's except for where it came from. So I'm going to plug in a negative 2 for this x and plug in a negative 2 for that other x. And here I get a negative 8 times the negative 1, so a positive 8. A negative 6 squared is 36. And that is 288 if I'm multiplying correctly, times x plus 2. And because of the exponent on the x plus 2 factor, what is that? So 1 that's implied. The behavior of our graph as we are approaching x equal to negative 2 is taking on the behavior of this positive slope line of a positive x, a very steep one, but a positive x. And we know a positive x graph would look something like that, sloping up from left to right. So if I kind of sketch a little positive slope line around x equal to a negative 2, and again over here, our overall behavior we said was a negative x even, a negative x squared, where the endpoints of our graph should be going down, like over here and over here. And so if we put all of those behaviors together, we said it's coming down as you went towards a negative infinity. We have this positive slope line as we are going through the x-intercept of a negative 2. There's got to be some sort of turning point for it to come back around, which is going to take this negative x cubed shape as we go through 0. There's got to be some sort of turning point for it to come back up towards this positive 4. Then it's taking this negative x squared shape as we approach that x-intercept of 4. And then it's coming back down, going towards a negative infinity as x's are getting larger and larger. And that would be the general shape of that graph on example 2. And I'll hold off on 3 and hold off on 4. So that you guys can try that. And I'm going to jump over to example 5. So example 5, again, we have another polynomial function. All of our exponents are non-negative integers. And we've got an x squared minus 1 quantity cubed. So I'm going to actually factor that out because we know x squared minus 1 is a differences of squares, and x plus 1, x minus 1. All of that was being cubed. So we're really looking at the factor of x plus 1 that's being cubed, the factor of x minus 1 that's being cubed, and then we have the term of x plus 3. So there is our polynomial. We first want to figure out what is the overall degree of that polynomial, and if we were to multiply out the entire thing, well, we would have an x cubed times another x cubed times an x to the first. So our overall degree, the overall power, would be an x to the 7th, and our leading coefficient is positive, or we have a positive x odd, and a positive x odd is going to look like a positive x cubed graph, which we know a positive x cubed graph is looking something like that. Whereas we go off towards a positive infinity, the ends of that graph are going up, the y values are going towards a positive infinity, and as our x's are going towards a negative infinity, our y values are going down towards a negative infinity. We have 3 x-intercepts. We have an x-intercept at or root at x equal to a negative 1. We have a root or x-intercept at x equal to a positive 1. And we have a root or an x-intercept at x equal to a negative 3. So I'm going to sketch those real quick on our graph. So an x-intercept at a -1, an x-intercept at a +1, and an x-intercept at a -3. If we said our overall behavior of our graph was taking on a positive x to the 7th or a positive x odd. So as we go towards a positive infinity, our graph should be coming up on the far right. And as we go towards a negative infinity, our graph should be coming down, because that is what a positive x cubed does. Instead of finding the specific behaviors, I'm just going to generalize. So I know that around my x-intercept of an x equal to a -3, it was being raised to the power of 1, which means around x equal to a -3, my graph should be taking on the shape of a line, because it's x to the 1st. And because my overall behavior of this positive x cubed, sorry about that, of that positive x cubed, my line would have to be a positive slope line in order for this graph to be coming down over here. And for my x equal to a -1 x-intercept, which is being raised to the 3rd power, my graph would have to be taking on an x cubed shape, and it would have to be a reflected x cubed shape in order for these two pieces to connect, and there cannot be any other x-intercept. And then for the x equal to 1, again, because this power of 3, an odd exponent, we know around x equal to 1, our graph again would have to take on an x cubed graph. And in order to connect with this piece over here, it would have to take on the shape of a positive x cubed. And we actually did not solve for our y-intercept. Our y-intercept, if I replace x with 0, I'm going to have a 1 cubed, which is 1 times a -1 cubed, so that's a -1 times 3. I'm going to get a -3, so we have a y-intercept here at a -3, so I'll kind of put that in there. And then we said that our graph should be coming up. So our overall graph is going to look something, and again, this is just a real general shape. But the more important part is the overall degree was an x cubed, so coming up over here on the right, going down over here on the left, and that our behaviors around the x equal to a -3 was linear, around x equal to a -1 was cubic, and around x equal to a +1 was a cubic. And we're just combining all of those behaviors together, which gives us our overall graph. Okay. And let's go to the last one on x equal, or number 6, where we are trying to now write a possible equation for our polynomial function. In terms of a possible equation for our for that picture there, well, first of all, we know that we have a couple of x-intercepts here. We have an x-intercept at a -4. We have an x-intercept here at a -1. And we have an x-intercept here at a +3. So in order to write the equation, I know I have to have a factor of x plus 4, which would give me that x-intercept of a -4. I have a factor of x plus 1 because of the x-intercept at x equal to a -1. And I have a factor of x minus 3 because of the x-intercept at a +3. I know that, again, we're just looking at a possible equation. At x equal to a +4, my graph is taking on this parabolic shape, this x squared type shape, which means that the exponent on our x plus 4 factor would have to be some sort of even integer. So that's why I'm just going to put a 2, but that's why it is a possible equation. I could have a 2, I could have a 4, I could have a 6, I could have any even exponent. Around the factor, the x-intercept of a -1, our graph is taking on a linear shape. And so if something is linear, that means it would have to be raised to the exponent of 1. And around our x equal to 3 x-intercept, our graph is taking on this cubic shape. So that means that on the factor of x minus 3, the multiplicity, the exponent, the power that it's raised to, would have to be something that is odd. And I'm just going to go with the smallest exponent of 3, but it could have been a 5, it could have been a 7. That's why, again, it's a possible equation. If we look at our overall graph, our ends of our graph, our end behavior, it is coming up here on the right and it's coming up here on the left. So our overall end behavior, our endpoints are coming up, which means that our overall degree should be something that is x even. And if we add 2 plus 1 plus 3, we're going to get an x to the 6. So what we have written is an agreement with the endpoints of our graph. We also know, because it's going up, that our a term needs to be positive. Well, we have a y-intercept over here, and that's looking like, what, a -27? So if our y-intercept is a -27, then I'm going to set my y value equal to a -27. We don't know what that a is, what that coefficient is that's in front. But for a y-intercept, if our y-intercept is at a -27, that means the x value needs to be 0. So I can think of that as 0 plus 4 quantity squared, and 0 plus 1 to the first power, and 0 minus 3 cubed. So we have a -27 is equal to a 16 times 1 times a -27, or we get 1 is equal to 16a, or our a term would have to be a positive 1/16. So a possible equation for this given graph could be f of x equal to a 1/16 x plus 4 quantity squared times x plus 1 times x minus 3 cubed. Again, possible because our exponents on our x plus 4 would just need to be some sort of even exponent. I just went with the smallest to make it easier. And on our x minus 3, it would just have to be something odd, and 3 is the smallest possible. We don't want 1 because 1 means then it would have to be linear. So it would have had to have been a 3 or 5 or higher. And that would have been our possible equation for this polynomial. So I am going to leave now numbers 3 and 4 for you guys to do. On 3, if you could, when you go to graph, try graphing and finding exact equations for your behaviors as we did here, and we were finding our exact behaviors as we did in example 2. And on 4, because your exponents are so large, the multiplicities are so large on those various x-intercepts, then just as I did on number 5, just use your end behavior and your individual behaviors, your general behaviors, to try to just sketch a graph without actually finding out these specific equations for the behaviors, because you're going to get too big of numbers for your exponents. Okay? Have fun, and we'll check in with you later.